Welcome to the lesson 24 of industrial instrumentation. In these lessons, we will consider piezoelectric sensors. Now, as you know, piezoelectric sensors is based on piezoelectric crystals, right. So, it has a property that if you apply a force across the surface of these piezoelectric crystals, I will get a voltage, and this process is reversible. That means, if I apply the voltage, I will get the force also. So, utilizing these principles, obviously I can make the sensors which can measure force, and piezoelectric crystals is extensively used for as I told you, that is reversible, that means it is extensively used for generations of the ultrasonic waves. As you know, there is ultrasonic sensors ultrasonic sensors are used extensively in the case of flow measurements and all these things, like ultrasonic flow meters are there. So, you have seen that actually there we are using the to launch the ultrasonic signals. We want that ultrasonics, piezoelectric sensor, piezoelectric crystals actually we have used there. So, it is another use, and also the piezoelectric crystals, as you know, it is used for measurements of for the generations of the very stabilized frequency, because it's piezoelectric crystal, if we will see later on that it has a if you draw the equivalent circuit, that you will find that it has a very high selectivity. It helps to make the oscillator which is very stable in frequency. These are the all different applications of the piezoelectric sensors. So, we will discuss one by one what are the and piezoelectric crystals. We will find that I need a special type of amplifier to those to amplify the charge generated across the plates of the piezoelectric crystals. Okay. So, let us look at the piezoelectric sensors and principle of operations. So, contents is not there. Contents, as I told you, we will discuss basically the piezoelectric sensors, its principle, and charge amplifier, and the crystals, piezoelectric crystals, that is as it is used in the making the sinusoidal oscillator, right. So, principle of operations of piezoelectric crystals. Let us look at. The piezoelectric sensors are based on the principles of electromechanical energy conversion. The mechanical input is converted to the electrical output, and that is the basis of these transducers, and this transducer shows piezoelectric effect. Okay. Actually, this is actually piezoelectric effect, that means if I apply some force, I will get some voltages. This particular effect is called the piezoelectric effect. Not all the material has some this effect. We will see that there are some synthetic materials which has this property. Also, there are some natural materials which has this property. Piezoelectric effect. What is the piezoelectric effect? When certain solid materials are deformed, they generate within them an electric charge. This effect is reversible, and thus if a charge is applied, the material will mechanically deform in response. These are known as a piezoelectric effect. Exactly this thing we did while we are making the ultrasonic sensors. Instead of steady voltages, what we are giving a time varying voltages across one plate. Obviously, the force which you will get, that is also time varying signals, and that can be that can be on the order of megahertz range, right. So, that we can get the ultrasonic signals from these piezoelectric sensors. Applications: measurement of acceleration, force. Also, it is extensively used in the vibration analysis. Okay, that is the only sensors which is used for the vibration, for crack detection, for thickness measurements, all those things you will find that it is used. For generating high voltage, because momentarily it will make a very high voltage, even though the current capability is very small, but I can generate a high voltage if I apply sudden high pressures, okay, or impact on the piezoelectric crystals. Obviously, the high voltage will be generated. And ultrasonics, right. These are the different, also we have not mentioned, so it is also extensively used, as I told you earlier at the beginning of the lesson, for making the crystal oscillator. Piezoelectric phenomena, let us look at historic background of these particular sensors. In 1880, Curie brothers discovered the direct piezoelectric effect in certain solid crystalline dielectric substances such as quartz. Quartz is a natural substance. We will see that quartz is not only the material which has a piezoelectric effect. There are many synthetic materials, which found later on, or the scientists have developed. We will see that in those piezoelectric materials, you can get the piezoelectric effect, right. Now, under stress free condition, what will happen? What is the under stress free? Let us look at the diagram. Under the stress free condition, what will happen to these piezoelectric sensors? You see, this is a total, this is silicon dioxide crystals. You see what will happen here. I have silicon, this is positive, and this is x axis, and this this is the silicon ion, this is the oxygen ion. So, the under stress free condition it will look like this, right. Now, what will happen now if a stress is applied on this particular crystals? Let us look at when the force along the x axis is applied. So, I will get a response like this one. If I take this is y x axis, this is as y axis, you see that if I apply some force, it will happen. Let me see. Yes, you see I am applying a force here, I can this. I am applying a force here, Also, obviously, if I put on a, obviously it will also make on the both sides. Actually, on the both sides, I am putting a pressure. So, what will happen? You see that these positive and negative ions will be distributed like this, right. This is along that x axis if I apply the pressure. Now, what will happen if I apply the force in the y axis? You see, this is the y axis and this is the x axis. This is the two plates A and B. Charge is developed on the two faces A and B, right. You can see that charges have been developed across the plates A and B, right. Positive charge will be developed here, negative charge will be developed here, right. The above is known as longitudinal effect. This is called the longitudinal effect. We have also transverse effect. Let us look at that. When the force along the y axis, if now suppose you apply the force along the y axis, then what will happen? If I apply the force along the y axis, let us look at. So, I am applying force in this direction, So, this is my y axis and this is x axis, right. But my plates are, I am collecting the charge from the plates which is placed on the x axis, right. So, what will happen? You see the positive charge will move in these directions and a negative charge will move in this direction. So, this will be positive plates and this will be negative plate, right. So, the stress which I am applying, this is sigma y, because that is sigma x. If you can look at, this is sigma x because this is applied here, right, applied in these x directions. And since it is direct in y directions we are applying, this stress is sigma y, clear. Now, charges are developed on the two faces A and B, same the charges in the previous case when you apply the x axis along the x axis or across the x axis, the charges will be developed is across A and B, and if you apply the stress in the y axis, the charges developed will also be on across the plates A and B. The above is known as transverse effect. One is the longitudinal effect, transverse effect. We are all familiar with this longitudinal and transverse because we have extensively these points have been discussed while we are we studied the lesson on the stress or on the strain gauges, right. Now, materials. What are the different materials which is used? For the piezoelectric crystals, because you know that previously this only quartz people thought of, that is the only has property. A quartz is quite expensive also. Quartz has a piezoelectric property. So, but later on we found that there are some synthetic materials also which has a piezoelectric property. Let us look at that. The materials that exhibit or that show a significant and useful piezoelectric effect fall under the three main groups. Okay, there are three main groups we can categorize. One is the natural, quartz and Rochelle salt are the two. Quartz is very commonly used and Rochelle salt is also used. Then you have synthetic, lithium sulfate, ammonium dihydrogen phosphate. These are the two different synthetic materials. It has also these two materials also have the property of the piezoelectric effect. That means, if you apply pressures, the voltage will be developed. If you apply the voltage, the pressure will be developed or force will be developed across the plates. Also, we have polarized ferroelectric crystals. These are barium titanate and lead zirconate titanate. This also coming under synthetic, but this property is something different. That is, we have put on the different categories, right. Because of their natural asymmetric structure, the crystal materials other than the ferroelectric crystals ferroelectric crystals show the effect without further processing. We do not need any further processing. You will see that if I have a natural asymmetric structure, then the crystal material other than the ferroelectric crystals show the effect without further processing. However, for ferroelectric crystals, they need to undergo certain processing. What are those? They must be artificially polarized by applying a strong electric field to the material while it is heated to the temperature above the Curie point of the material. They are then slowly cooled with the field still applied. When the external field is removed, they have a remained polarization which allows them to show the piezoelectric effect or exhibit the piezoelectric effect. Okay? This is the thing we will have. Now, as piezoelectric transducers, if I look at actually naturally available transducers, you see that what are the different axes. We are taking one. You see, these are all, I mean, in these directions, and all this arrow is actually the shear stress which is developed across the different axes of the piezoelectric crystals. Okay. These are the force, typical, tensile or compressive, these are the shear. So, direction 1, 2, 3 are the compressions or tension, either compressive force can be tension, tensile force, both cases you will get a piezoelectric effect, and 4, 5, 6 are the shear stress on the piezoelectric crystals, right. Now, you see this is the typical piezoelectric, I mean I should say the schematic of the piezoelectric crystals as it looks like. I can take the axis like this is x axis, this is y axis, this is z axis, or this is 1, 2 as it happened here. Let us see. So, 1, 2, 3 in this case also I can show that this is 1, this is 2 and this is 3, right, like this one. So, this is 1, this is 2 and this is 3. So, we have a shear also, right. So, the dimensions you see, the width of the crystals is W, its thickness is T and its length is L, right. So, we have two electrodes, we have seen the two electrodes, one in this and another one this one. So, we are taking out this voltage U, right. So, we applied force Fi across these plates, right. Now, there are two families of constants, G constants and D constants, which are used to describe the piezoelectric effect, right. So, we will discuss two constants, these are necessary, or as I should say the parameters of the piezoelectric crystals by which we can define a piezoelectric crystals. So, that is the reason I am telling there are two families of constants, G constants and D constants, which are used to describe the piezoelectric effect. So, Gij and Dij, what are these? Where I is the direction of the electric effect and J is the direction of the mechanical effect, fine. So, G constant is defined as G33 field produced in direction 3 divided by stress applied for direction 3, right. So, field produced, that is voltage E naught divided by T thickness, and stress means force applied Pi across that divided by area, is not it. You see the force applied is Pi and what is the width W into L, that is the area of cross section. So, if I divide Fi by, so I will get a stress Fi divided by W into L, I will get stress, and by E naught divided by T, so I will get the field, is not it. So, E naught by T upon Fi by WL. Now, D constant is defined as D33 charge generated in direction 3 divided by force applied in direction 3, which can be written as Q divided by Fi, right. That means the charge developed divided by the force applied. Moreover, P is equal to D multiplied by sigma, right, where P is the polarization and sigma is the stress, and D is we call the sensitivity matrix of the piezoelectric crystals, right. Equivalent circuits of the piezoelectric, I mean for this one you see like this one. So, we have a crystals, okay. Then we have a you see that these are crystals, this is a charge, I mean equivalent circuit in not that sense. I mean if I replace this piezoelectric crystals by a signal generator, the circuit will look like this one. So, I have a signal generator, voltage source, of Q, charge source, then we have the resistance R crystals in parallel with the capacitance, that means C crystals or CR. So, crystals we are taking the first 3 letters crystal. So, I am taking first 3 letters C R Y, clear. Now, C R Y is the leakage resistance, which is extremely high, is 10 to the power 12 ohm, or is 1000 gig ohm I should say, and C crystals is equal to epsilon into WL by T. Typical dimensions of a expression for a capacitance, right. WL is the area of cross sections of the capacitance if I consider it as a parallel plate capacitors, T is the thickness, and epsilon is the permittivity of the medium, right, or dielectric constant of the medium, and Q is the charge generated, right. So, the Q charge generated, R crystals leakage resistance which is around 1000 gig ohm, and C crystals equivalent capacitance of the crystals equal to epsilon WL divided by T, and Q is the charge generated. Measuring circuit we have like this one. So, we have a crystals, we have a cable, but there must be some cable, some wire is to be connected, and it is connected to the amplifier, so that I will get the output E naught. Now, this is the complete circuit of an piezoelectric crystals along with the if you think of as a charge generated along with an amplifier. So, all the impedance of the amplifier also should come in the picture of the equivalent circuit, right. So, here you will see we have Q, R crystals, that means leakage resistance of the crystals, C CRY capacitance, C is the cable capacitance which is coming across, R is the amplifier impedance, and is the input impedance, capacitance of the, because as you know in any amplifier has capacitive range at which actually you will get that particular input impedance. So, that impedance with capacitance must be mentioned also in the equivalent circuit. Now, you see we have simplified the circuits. What we have, you see here we have 3 capacitances and 2 resistances. This we have combined to an equivalent capacitances. We are writing C and R, and what is C and R? Let us look at. So, this is C, all the capacitors are combined here and all the resistance are combined here. We are getting the output voltage U and the charge generated Q, right. Let us look at. So, charge generated Q. So, C equal to C crystals plus C cable capacitance plus C amplifiers, all will come in parallel. Then since it is in parallel, all will be added, all the capacitance value will be added, and R is the R crystals resistance in parallel with the amplifier resistance. So, E naught I can obviously write small I into R equal to dq by dt minus C to dE naught by dt whole multiplied into R, or RC equal to RC multiplied by dE naught by dt plus E naught equal to R dq by dt. So, E naught by Q, because Q is the input, we assume that the Q is generated, and what is the output, so let us look at. So, the sensitivity will be E naught by Qs in S domain, R into S divided by RCS plus 1, right. This where Q equal to D into F, where E naught by F S, that is E naught, because as you know Q is equal to D into multiplied by F, where E naught is equal to E naught divided by F, that is actually this that should be the sensitivity, because actually we are applying the force. Force is generating the charge, right. So, actual sensitivity, if you want to we have to find not the E naught by Q, we have to find the E naught by F actually, the output voltage divided by the force which you have applied equal to D into R into S equal to by RCS plus 1. This we can write D by C into tau S into 1 plus tau into S, right, where tau equal to R into C, clear. The above represents a high pass transfer functions of this. So, it looks like it is not possible to measure any static force with these circuits. Please note, the static is not possible, so only in the dynamic, whenever there is a change in the force, or then only I can measure, I will get the output, otherwise we will not get any output. Static sensitivity D by C will change with the change in any of the values of C cable capacitance, cable capacitance and C amplifier. Okay, so it is sensitive to this, so this must be constant. For the reason we use a charge amplifier, so you see, so it is not possible to keep all these things constant, so it is better if you use a charge amplifier. Measurement using the charge amplifier, the charge amplifier looks like this, we have a Q and we have a R and C. At the input sides, on the feedback side we have feedback resistance RF and the feedback capacitance CF, and we are using operation amplifier, right. So, this is the basic charge amplifier. Now, from circuit analysis we can say that the dq by dt equal to minus E naught by RF minus CF into dE naught by dt. So, this will give you RF into CF into dE naught by dt plus E naught minus RF into dq by dt, just algebraic manipulations we are doing, or we can write EQ by E naught by Q in S domain plus E naught equal to minus RFS upon 1 plus RF CF into S, and E naught by F S equal to minus D by CF tau Fs 1 plus tau Fs, where tau F equal to RF into CF. The above circuit also cannot measure static force, but it removes the dependencies on the cable capacitance and the resistance, right. So, what is the cable capacitance? All this thing will come in the picture. Now, piezoelectric accelerometer if you look at, so the basic block diagrams of the piezoelectric. So, because piezoelectric crystals are used as an accelerometer, so we can make a integration of that, we will get velocity. If you make another integration, so I get a displacement, right. On vibration analysis, as you know, it is extensively used as a piezoelectric sensor to pick up the vibration. So, the basic block diagram, so I have a seismic transducers, okay, K stiffness of the crystals, okay, piezoelectric transducers, this is and the output voltage we are getting E naught. Now, for a seismic transducers, we know that X naught by AI S equal to 1 upon S square plus 2 xi omega n S plus omega n square, right. For piezoelectric transducers, we have E naught upon Fi S into D by C tau S 1 plus tau S, where tau equal to RC and D is the sensitivity. Now, I can write, I just make the little manipulations, E naught by AI S domain, E naught by Fi into Fi by X naught into X naught by AI. So, ultimately I am interested E naught by, this will all cancel out, E naught, this will cancel out, this and this will cancel out. So, only E naught by AI will remain. So, this is, if I substitute separately E naught by Fi, Fi by X naught and X naught by AI, I will get these whole expressions, you see, I will get these whole expressions. Clear? D by C tau S 1 plus tau S into K into 1 plus S square plus 2 xi omega n S plus omega n square. Now, E naught by F input S equal to 1 by M E naught by AI into S. This I can write D by C into tau S 1 plus tau S multiplied by K by M into 1 upon S square plus 2 xi omega n S plus omega n square equal to D by C tau S 1 plus tau S omega n square S square plus 2 xi omega n S plus omega n square, right. The response curve will look like this one, that means that the output voltage divided by F input, that means force, it will look like this. This is the highest point D by C, we are plotting omega here, okay. So, it is almost as a band pass characteristics, you can see with certain hump. So, after that natural frequency, because at the natural frequency there will be some hump at resonance. So, after that it is falling down, right. at 1 by tau. So, I am getting the outputs, the mod of E naught output voltage divided by the force in j omega domains will be d by c, right. So, this is the response of the piezoelectric crystals. Now, as I told you that oscillators are different types, and now piezoelectric crystals also has a tremendous applications in making oscillators. We are not discussing about the piezoelectric crystals as it is used as a generation of the ultrasonic waves. When we have discussed the ultrasonics, we have seen that what are the different, how can you generate all these things, ultrasonic waves. And but crystal oscillator is a very one of the common, almost all of you are using some quartz watch. What is the quartz it is written? You see it is written quartz. It's not that just to attract the customers and increase the price of the watch. Actually, this is used for watch or wall clock. Everywhere you will find it is written quartz. That means that they are using some oscillators, because ultimately in all electronics watch or clock you need some a basic oscillators, right. So, that will drive some stepper motors. So, that will be incremented, it will step change by for each signals it will change like this one. So, that the seconds arm will move, subsequently it will move the minutes arm and further the hour arm, right, with the gear arrangement. Now, but basically I need an oscillator. Now, if I use, what is the problem if I use, suppose if you use an oscillator based on 555 or any others, you can use 2 transistors also to make an astable oscillators, or you can make an op amp to make a astable oscillators. Not necessarily I need sinusoidal oscillation there, right. But the thing is there, you know, that if you make that type of oscillators, it heavily depends on the, not only depends on the type of the resistance capacitance, it depends on the absolute value of the resistance and capacitance. And as you know that as the time goes by, so this may change, right, this value of R and C may change. So, that will change the ultimate the clock, the period of the clock. So, if it changes, obviously your watch or clock will no more remain accurate. So, for that reason people use a crystal, because as you know crystal is a property. If you draw the equivalent circuits of crystals, you will find there is a very high value of inductance we know. As you know the inductance, if you have any coil has a large inductance, obviously its Q will be quotient point will be very high, right. So, if the Q is high, obviously if I use some oscillator circuit based on these particular crystals, obviously what will that time you should not see as a crystal. So, you will say you should look at a passive circuits which has a high value of inductance. If the inductance is very high, obviously what will happen, you know, that I will get the large value of the Q. So, this large value of the Q means I will get a tremendous amount of frequency stability of the circuit, right. So, let us look at that. You see two piezoelectric crystals with the electrodes plated on the opposite faces, a potential applied between the electrodes, we know. Forces are exerted on the bound charges within the crystal. An electromechanical system is thus formed which will vibrate when properly excited, right. A electromechanical system is thus formed which will vibrate when properly excited. The equivalent circuit is like this one, you see. I have a inductance, let us look at, I have an inductance L, then I have an inductance L, I have a resistance R, C, and also a parallel capacitance C dash. This value of L is very high in the case of piezoelectric crystals. That makes the frequency stability excellent. Otherwise, nobody should care for these quartz crystals, right. Now, neglecting R, if I neglect R, the impedance of the crystal is a reactance which can be given as J by omega C into omega square minus omega S square upon omega square minus omega P square, where omega S and omega P are the series and the parallel resonance of the circuit, where omega S 1 by L C and omega P equal to 1 by L C plus 1 by L C dash, right. Omega S, as I just right now told, the series resonant frequency, and omega P is the parallel resonant frequency. Okay, these are the one is the series resonance and is the parallel resonance frequency. frequency. So, what will happen actually, since the C dash is much greater than C, omega p is almost equal to omega s, right. So, if it is omega p omega s, reactance as a function of frequency, you see if I plot this one, it will look like this one. This is inductive here, and here you see it is capacitive. Omega is series resonance, omega p is a parallel resonance. Okay. So, this is the, if I plot the reactance of the piezoelectric crystals versus frequency, I will get a response like this one, right. Now, the crystal reactance as well as that of the LC network must be inductive, quite obviously. Basically, crystal, your piezoelectric crystals, you can see if you look at from the basic point of view, is nothing but an LC oscillators. We have studied the LC oscillators in our analog electronics. You see, it's simply the LC oscillators. Only thing that L is replaced by the piezoelectric crystals. For the loop gain to be greater than unity, the oscillation frequency must lie between omega s and omega p, but closer to omega p. So, the loop gain we have seen, you see, that means it should lie between omega s and omega p, but closer to omega p. If it is there, so no problem, I can purposefully choose that thing. Since omega p is almost equal to omega s, the oscillator frequency is fully dependent on the crystals and not on the rest of the circuit. This is the most important point of the piezoelectric crystals. You see here, since omega p is equal to omega s, the oscillator frequency is fully dependent on the crystals and not on the rest of the circuit, because you need a rest of the circuits. We will find that we have other elements in the circuit, but the frequency will not depend, the frequency of the crystals or frequency of oscillation of the oscillator will not depend on the rest of the circuits, it will depend only on the crystal itself, and it is highly stabilized, it hardly changes with time or anything. So, that is the reason I get a very stable frequency there. So, all these properties happens because of large inductance. Now, let us look at a FET crystals oscillator shown in this next. We see that there is a how using a FET, it is basically a Colpitts oscillators. We can see this is a typical Colpitts oscillators, you can see here. So, I have a crystals here, I have a 10 mega ohm resistance, and I am using a transistors 2N2608, and these are tank circuits which value 61 to 122 microfarads with 300 picofarad capacitances, emitter bypass capacitor 0.02 microfarads, and the resistance, emitter resistance of 2.2 mega ohm. So, this, but please note that the piezoelectric crystal does not necessarily mean that it will have totally independent of temperatures. Okay, it has temperature dependency, but you see the advantage of this one, this 10 mega ohm, 2.2 mega ohm capacitance value, all these things, whatever the things, and you see the inductance here is very small, 1 or 2 turns of coil can generate this type of inductance. So, what will happen, you know that in these cases, in this entire things, what will happen, this oscillation frequency does not depend on this resistance, capacitance and all these things. It will depend totally on the crystals, and crystals, that parameters does not change, right. So, obviously, by this I can get a very stable signals from the circuit. We know, as you know, there are many other oscillators. We have a sinusoidal, we have a Wien-Bridge oscillators, because basic in all oscillators, as you know, the basic mother of all the function generation is the sine wave, because once you get the sine wave, I can pass through a Schmidt trigger. So, I can make a square wave. If you differentiate a square wave, I will get a pulse. If you integrate a square wave, I will get a it looks like this. You see that if I have a sinusoidal wave, I should take some other color. So, I get a square wave like this, a sinusoidal wave. Okay. There are various types of oscillators. We know Wien-Bridge oscillators, okay. Then phase shift oscillators, Colpitts oscillators. So, these are the different types of oscillators available. Now, these signals, sinusoidal signals, okay, if I pass through a Schmidt trigger, I will get a signal like this one, right. If I chop the other parts, I will get a signal like this one, lower part, right. If you do not have a dual supply, so I will get, if it is 0, so it will not. Now, if I integrate these signals, how will I get the signal? I will get the signal like this, is not it? So, I get a triangular wave. Now, if I differentiate this signal omega, what I will get? I will get a pulse like this one, is not it? So, this will, I mean, this is the base. So, the basic of the all the signal generator is basically sinusoidal wave that we have seen, right. But as you know that in the crystal oscillators also we are basically generating sinusoidal wave. Then we are passing through a Schmitter, we are making a square wave. So, there are many, I mean, Wien-Witch oscillators. Why you should ask, why should we go for crystal oscillators as a piezoelectric based sensors, piezoelectric based oscillator? Because of the frequency stability. In Wien-Witch oscillators or a phase shift oscillator, you won't get that type of good stability, right. So, as you can see in these particular lessons, we have discussed the basic piezoelectric sensors, its structure, crystal structures, how we can apply the force, how we will get the signals, what is the charge amplifiers that we have discussed, and what is the problem with the simple amplifiers, it heavily dependence on the cable capacitance, cable resistance, that can be avoided if I use a charge amplifier. So, those type of things we have discussed in this particular lesson. Also, we have discussed that a piezoelectric sensor, I am not going to the vibration analysis, all those things, but piezoelectric crystals are also used for vibration analysis, crack detections and all these things. In continuation of the lesson 24, we will discuss now the flapper nozzle systems. As you know, flapper nozzle is a pneumatic systems. It is extensively used in the pneumatic transmitters and all these type of things. Actually, you will get a small displacements can be converted into a large pressure change, right. And as you know that in some industries it is still forbidden to use the electrical systems, though the transmitters are electrical, but the large torque which are necessary for controlling the valves and all these things cannot be provided by the electrical systems of supply of 40 volt or something, and you cannot use more than 40 volt there. So, that is a problem. So, what happens there, they still use those pneumatic systems. So, flapper nozzles is a part of that. So, I will discuss what is the flapper nozzle systems. A flapper nozzle system is used for the measurement of minute displacements. A small movement of the flapper can result in a large change in the output pressure, and hence it is treated as displacement to pressure converter. That means displacement can be converted to the pneumatic pressure, right. So, it is total pneumatic systems, you can see here. Such a transducers are designed for use in both hydraulic and pneumatic power supplies. As though the pneumatic system is operated at an air pressure range of 3 to 15 psi, as you know that though we use SI systems in academics, still in industry they use those terms like 3 to 15 psi. As you know that 3 to 15 psi is standard for pneumatic systems, which corresponds to 4 to 20 milliampere of current in the electrical domain. Now, flapper nozzle systems, let us look at, you see this is our flapper nozzle systems. We have a flapper. You see this is even though we have shown it's usually very thin, right, and there is a nozzle. Nozzle also diameter is very small, right. Now, what will happen, you know that if this flapper goes like this, or this, so a large pressures will develop in the systems, right, at here. Here we are giving some continuous supply of pressures. Now, if it moves away, what will happen? If it moves away, the pressure will be less. So, this displacement, small displacement can be measured by the pressure, measuring the pressure at this point, right. And also we can see you can use a feedback control systems with the flapper nozzles, because it can have a automatic feedback systems. That means that you have, if I use a if I suppose if this nozzles is coming very close to this one, automatically the pressure will increase and it will give the back pressures here. So, it will put the nozzles in a particular position. That is the feedback systems. Anyway, let us look at Now, you see this is our this is a P ambient pressure. I have a flapper. This, as I told you, is a very thin actually, though it is shown. So it can move like this. It can move like this. That means flapper can move like this. So it is very thin. So flapper can move like this. So like this one. So it is like this one flapper. So it will move like this. I have a hinge here. So nozzle here. Okay, it will move like this. If the flapper comes very close to the nozzle, the pressure will increase, PO will increase. If it goes away, PO will decrease. That is the basic principle of the flapper nozzle systems. And we have also at the end of the nozzle a fixed pressure supply or air supply, right? P is the ambient pressure, then Xi is the displacement of the flapper, Gu is the outlet mass flow, Gs is the inlet mass flow, and PS, T is the inlet pressures and the temperature. PO is the pressure output at temperature T0 obviously. The output pressure of the nozzle back chamber is measured by a pressure measuring device. As you know that you can measure by there are so many gauges we have studied so far, with the bellow gauges or with the Booth gauges or the diaphragm gauges we can measure, and that pressure can be calibrated in terms of displacements of the flapper, right? The flapper nozzle system shown in the figure consists of a chamber of small volume connected to a constant pressure source on one side and vented on the other side to the atmosphere through the nozzle. Let us look at it again. You see. So constant pressure source is this one, GS and PST. This is our constant pressure source. Right here you see. This is our constant pressure source. This part, it is connected to. So you see, this is a nozzle. This is a one part is nozzle. This is free. Continuous air is leaking through this one, and this is a continuous supply, and this is actually measuring the pressure, which corresponds to the display, corresponds to the position of the flapper, right? So the output pressure of the nozzle back chamber is measured by a pressure measuring devices. As I told you, the flapper nozzle system shown in the figure consists of a chamber of small volume connected to a constant pressure source on one side and vented on the other side to the atmosphere through a nozzle. The flapper held in front of the nozzle is used to regulate the rate of fluid flow bleeding out through the nozzle to the atmosphere, right? There is a continuous leak of air or bleeding of air to the nozzle, right? That is actually we are telling here. The flapper held in front of the nozzle is used to regulate the rate of fluid flow bleeding out to the nozzle to the atmosphere. When the flapper is held tightly against the nozzle, no fluid leaks out, and ultimately the output pressure PO reaches the value of the supply pressure PS. Is not it? Let us look at what is that. What I am saying that when this flapper, you see, when this flapper comes very close to the nozzle, when this flapper very close, so these pressures and this PS will remain same. PS and PO will be same at that point, right? If it is coming, but if it goes away, it will not be the same. When the flapper is held tightly against the nozzle, no fluid leaks out, and ultimately the output pressure PO reaches the value supply pressure PS, right? Now, when the flapper is held too far away, it has no effect on the output flow rate, and the flow rate is governed by the system size and configuration. Quite obviously, at the same time there is no control. And as the system is designed for the measurement of displacement, the supply side restrictor and the nozzle are so designed that the output pressure never falls to the atmospheric pressure, even with the flapper held far away, right? That's the way we have to do, otherwise there will be a problem. Now, flapper nozzle characteristics, you see, this is our flapper nozzle characteristics. This is output pressure divided by the supply pressures. In the x-axis the displacement. What is the displacement? Displacement of the flapper. So, pressure change versus displacement. This is a normalized, so PO by PS. The above show a small change in the displacement produces large output change. You see that in this region, you see for a small change in output, for a small change in displacements, I am getting a large change in the ratio of the output pressures and the supply pressure, right? Now, supply side restrictors, we have a supply side restrictors also. You see here the choked flow, it is the actually operating point of our this is our operating point where the slope of KSF, and this is a subsonic, this is unchoked flow, and we have a choked flow which is sonic flow, right. So, here we are plotting PO or output pressure. In the neighborhood of the operating point, we can do a linear approximation, otherwise it is non-linear as you can see, but at the neighborhood of the operating point of our flapper nozzle systems, we can consider it as a linear sensor. So, GS equal to GSPO, which can be almost approximated GSO plus derivative of GS by dPO at the point PO equal to P00, and PO minus P0 equal to GSO plus KSF plus PO into POF, OP. GSO is the value of GS at equilibrium operating point, PO is the value of PO at equilibrium operating point, and P0P is a small change in PO from P00, right. And KSF value of derivative of GS with respect to PO at operating point. And load side restriction, let us look at. So, this is the load side restriction graph. So, we have GU here and we have plotted PU here for different values of Xi, right. So, we can also see for the small region we can linearize. So, if there is operating point, we can linearize across this, right. Here GU equal to GUPO Xi equal to GUO plus KNP POP plus KNX XIP, where GUS is the value of GU at equilibrium operating point and XIP is the small departure from the equilibrium operating point Xi 0. Therefore, I can write GU equal to GU naught GU 0 plus delta GU with respect to delta GU by delta PO at Xi at x equal to I 0 P 0 0 multiplied by P0 minus P0 plus delta GU by delta Xi Xi comma 0 P0 comma 0 Xi minus Xi 0. Now, we know that mass in equal to mass out, if mass in minus mass out is the additional mass stored, right. So, GSO plus KSF multiplied by POP dt minus GUO plus KNP POP plus KNX XIP dt, which I can write DMP equal to VRTO multiplied by dPO, where since P0V equal to MRT0. Let us assume that GSO equal to G subscript TO, then I can write V by RTO dP0P by dt plus KNP minus KSF P0P plus KNX XIP equal to 0. Let take K equal to minus KNX upon KNP minus KSF PSI per inch, at tau equal to V by RT KNP minus KSF, then I can write tau S plus 1 P0P equal to KXIP, or P0P upon KXIP equal to capital K by tau S plus 1. Thus, we see that the above is a first order system. So, flapper nozzle systems is a first order systems. So, it is also reverse kind of transducers, right. So, process is reversible. That means, if the flapper comes very close, automatically the pressure will increase, or if the pressure increases, the flapper will go away. It is, I mean, from the nozzle, sorry. It is very fast active amplifier with good resolution. That is most important thing. It is a very fast active, even though it is pneumatic system, it is system is quite fast. Used in precision gauging, that means for a small displacements I can use this method. Constructions, let us look at. Nozzle diameter is usually 0.8 millimeter. The volume is 16 cc. Supply orifice diameter is 0.4 millimeter, okay, and fixed side restrictions. Value of K equal to 8000 psi per inch. So, equivalent circuit, if I look at, if you draw the equivalent circuits, it is Ri parallel with CO with a parallel Ri in series with CO, parallel with RO, which is variable. This is output. So, this is input, this is output. So, RO is the variable restrictions, Ri is the fixed restrictions, C is the capacity of the system or volume, and the transfer function of the electrical system is given by VO by VI S RO upon Ri plus RO multiplied by 1 upon 1 plus SC RO Ri upon RO plus Ri, right. Some applications, let us look at force balance differential pressure transducers. It is extensively used. Okay. You see, this is the force balance. We have two bellows here. You see here two bellows. Okay, pressure P1 and P2 we are giving, and this is a pivot, and there is another bellow here, and this is my flapper nozzle systems here. You see that this is flapper. So across this pivot, so this can move. So hinge here, so this flapper can move this and this direction, right. So bringing this flapper very close to nozzle or going far up the nozzle, right. You see it cannot go very far. What will happen? You see if it go far, okay. So you see if it comes very close, it cannot close it. It cannot be restrict this one because there is a feedback below, so it will push this upward. Because if it comes out, automatically the pressure here will increase, so it will go to the feedback below, okay, so it will increase, right. Now if what will happen, you see that if it goes far away, it cannot go far away also, because in that case it will also, this pressure will increase, so stabilizations will come. So regulated supply is coming P0 equal to K P1 minus P2. So you see this is a P1 and this is P2 coming through two differential pressures, right. The block diagrammatic representations of the above, you see like this one, P1 P2 AB1 AB2, like this one KB I1 AB2. So AB1 AB2 area of the bellows, KB is a bellows linkage compliance, Kn is a flapper nozzle gain. In the above circuits, P1 greater than P2, then the upper bellow exerts more force than the lower one. Thus the flapper moves away from the nozzle, right, because since we have a right side, we have below. So you see it looks like this, is not it? I have a bellow here, there is a flapper, I have a bellow here, I have a bellow. So this is P1, this is P2, and I have a nozzle here. Sorry, is not it? So what will happen if the flapper moves away from the nozzle and pressure inside the tube A falls. So suppose if this comes, then what will happen? Pressure, this bellows will, because this is a pivot, so this will, the bellow will, the flapper will move in this direction, so the pressure will fall, inside pressure of the orifice will, this nozzle will fall, is not it? The feedback bellow cannot hold the flapper in such a position and brings it down. The output pressures P0 equal to AB1 L1 by L2 by AB2 P1 minus P2. Flapper type servo valve, you see in this type of valve the sliding spool is actuated by a pressure difference at the two ends. When a signal to the electromagnetic coil moves the armature, the flapper moves towards one of the nozzle. The balance of the flow is changed throughout the orifice and it causes the pressure to increase at one end of the spool and decreases at the other. The spool moves until the pressure difference is balanced by the tension of the spool springs. An internal feedback provided by means of the mechanical linkage from the spool to the flapper. You see this is our entire flapper nozzle systems, right? This is a flapper nozzle servo valve. You see here, okay, this is our orifice, right? This is our flapper valve, okay, so this is electromagnetic coils, this is armature, right? So this is our springs on the both sides. You can see here the springs are on the both sides, this side, we have also springs, and this is our flapper valve, right? So in this lesson we will see that at the first part of the lessons we have discussed the basically the piezoelectric sensors, which is used for the measurements of the displacements, accelerations, which can be used as ultrasonic generations of the frequencies or ultrasonic waves, and also it can be used in the crystal oscillator. And the second part we have discussed a very important pneumatic system, which is called the flapper nozzle systems with the feedback systems, right. And it's very fail safe devices, as you can, if you compare with electrical devices, it never fails actually, this flapper, except the routine maintenance of the orifice, because entire operation depends on the orifice width also. So diameter of the orifice is also very important. It should, after over the long use, it should not widen, so that you have to change, you have to make the change in entire calibration. Otherwise, it is a just fail safe devices. It never happens that it is not working or it fails. So that is a great advantage of this type of pneumatic system. For this reason, it is used over the years in the industry, and still it is used in some of the industries like hydrocarbon industries, where high voltage is restricted. That means I cannot use a voltage or any devices which has a voltage more than 40 volt, because you know there is a large, if you have a large actuator or large valve control valve, I need the voltage at least up to 20 volt to create a large torque. That is not possible, because that voltage is not allowed in the hydrocarbon industry. Though the transmitters are electrical, that is fine, but the basic actuator, basic sensors there are the basic pneumatic, because it is totally hazardous free, right, because only supply we have instead of electrical supply. So we have a pneumatic supply there, right. So with this I come to the end of the lesson 24. Welcome to the lesson 25 of industrial instrumentation. In this lesson, we will consider ultrasonic sensor, right. Ultrasonic sensors, ultrasonic measurements of flow velocity or ultrasonic based flow velocity we have discussed some time back, but in these particular lessons we will basically will discuss the basic principle of the sensors, and how the transmitters, what is the principle of transmitters, its equivalent circuits, how the receiver works, and the various applications of the ultrasonic sensors like level measurements, crack detection, as well as the biomedical applications where the ultrasonic sensor plays a great role. So that part we will discuss in this particular lesson. Let us look at the contents of this lesson. Contents looks like ultrasonic principle, what is the principle, how it works, that is actually we will discuss here. Then transmitter receiver we will discuss in details. Then equivalent circuit of the ultrasonic sensors we will discuss. Then its applications, both the level measurements, crack detection, as well as biomedical applications, we will all discuss in this particular lesson.